What's up to you all matriculants? Welcome to it. This is Learn Extra with me, AB, and John. We're about to learn more and learn extra. And we're not going to waste any further more time because the show is hot and John is ready to teach you guys. John?
Thank you, AB. Great to be with you. At least we've put on the air conditioner now so AB can cool down. He really has been hot tonight.
Sure.
Even though it's been winter outside, he was complaining of the heat. So, guys, just cool him down. Don't get him excited. Okay.
They must get me excited, John. What do you mean? I don't want to be bored.
Okay, guys, Doppler effect. So what are we dealing with tonight? That's exactly it, the topic. It's all about what happens to waves, sound, and light in different circumstances. And it's a really key section. Now, good news for you, grade 12s, is that this section of work has got a little bit easier for the grade 12 exams because they've taken some stuff and pushed it to grade 11 and left you to focus on the Doppler effect. So we don't have to deal with too much as far as this topic of wave, sound, and light is concerned. The main focus is all about the Doppler effect. So there are some very interesting questions. Make sure you go back to the past exam papers and pull out as many of the questions about ambulances moving towards people, doves singing, dolphins doing all sorts. That's what we're talking about. Have you heard the Doppler effect?
Yes, I've heard about it, John.
You've heard about it, but have you heard it?
I think I've heard it.
So have you been standing on the side of the road when you've
Next
heard
to cars.
a car coming by or a siren coming by?
Yes.
That's an example of the Doppler
Every
effect.
day.
Okay, you might hear it every day. The change in the sound. How does it change? Gets higher or lower depending on the motion. But we'll come to that. AB, you give us some more.
I'm so ready to learn. Hey, John, it's going to be an interesting show. But my answer is get your notes. I am about to post the notes on facebook.com/learnextra. It's two options, the viewing option and the download option. And also the link to the test yourself questions, where if you get the right answers, the most correct answers before 12 o'clock on Friday, you stand a chance of winning this awesome Casio calculator. It's awesome. John always uses this calculator, and all our teachers always use the simulation of this calculator. So it's an awesome calculator. I'll be announcing the winner from last week's show. So keep it tuned in on the show. Isn't it lovely, John? Like this.
Very nice. And we're really grateful to Casio for making these available. They're going to be distributing the prizes as well. So good luck to you. Make sure you enter. And the most important thing, guys, if you don't win, it doesn't matter. You've learned something. You've done some brain racking and answering some of these great test yourself questions.
So true. And already I have mine, my sisters, just to calculate tax.
Absolutely. You're going to need to do that. You earn so much.
I'm going to do that. But otherwise, my sisters, if you're struggling anywhere, go to Facebook or follow us on Twitter @LearnExtra. John?
Okay, guys, thank you. Let's get through it. We need to be able to describe in both words and equations this thing called the Doppler effect. Now, there are a number of ways that you can see it, you can experience it, and it's really quite an amazing thing. I don't know if you've had the chance to do this, but perhaps you could try. But please don't get yourself into trouble, okay? So I'm going to tell you something now, but ask permission before you do it. If you can get some hose, some garden hose, preferably a piece that's got a little hole in it, and you cut off the garden hose, and you then clear an area away so you don't hit somebody, and you just swing it above your head, okay? You know what you'll hear? You'll hear this woo. It's right, eh?
Yeah.
You'll hear the woo, and if you got somebody to stand a little bit away, they will hear that sound goes woo, woo, and that's the changing pitch. So what we'll need to recognize is some stuff that you learnt in grade 11 with respect to sound, and we'll revise that shortly. The difference between, or the relationship between amplitude and loudness and frequency and pitch. But I'm getting ahead of myself. Let's first of all go and have a look at the challenge question. Okay, I will post this during the break, but let's just read it through now and make sure you've got it. It tells us the speed of sound is 340 meters per second in air. Now, guys, if they don't give you this in a question in a test or exam, you may assume that the normal speed of sound in air at a certain temperature is taken to be 340 meters per second. It can change. It can be 330 or it can be 350 depending on temperature. But if you say let's assume that the speed of sound in air is 340, you will get credit for your working. So now we've given that. Tells us how fast must a car go for a person standing on the side of the road to observe a frequency 15% higher than the engine's actual pitch. Okay, so what we need to recognize is that there is a change in frequency, and we want that to be 15% higher than the actual pitch. And there you've got it. The hint is very clear. Frequency is related to pitch. So let's get through our description. In the notes, what we recognize is what is the Doppler effect. The Doppler effect is the apparent change in frequency. Is the frequency really changing? No. The frequency of the source is staying the same. But what we recognize is that the person that is observing, that is standing away from the source, that's hearing or observing in a different way, it doesn't only have to be sound, they will appear to see something different or hear something different. They will appear to hear a change in frequency, which can also be reported as a change in wavelength. If the observer and the source are moving relative to each other. And now, here's the important thing. If they're moving together at the same frequency, or they're just standing stationary, then there will not appear to be any difference. But if they're moving either towards each other or away from each other in different directions, then we will notice a change in pitch. And that's what Doppler effect is right. So we are going to look at it. It's normally dealt with in sound, but guys, you don't only have to do it in sound. You can even do this in your bath. Okay? Yes, you can. If you take your bath and you take a stone or a weight, attach a piece of string to it, and you just simply lift the stone up and down. Okay? That will generate some circular waves. And what you will see is that these circular waves will start at a point and they will move out in your bath, spreading out. If you've got a light shining in your bath, you might even look at the bottom of your bath and you will see regions of bright and dark shadows. Regions of light, bright light, and then a region of shadow followed by a region of light, and so on. And it will spread out across your bath. Now, if instead of keeping that stick stationary, you move it up and down the bath, watch what happens to the pattern. And I'm going to draw it very quickly for you because I like to just show you the ideas that you're going to get. If this thing is moving, if it's stationary, you would get pattern like this. Just circular pattern. And I've drawn not very well because these should be circles and they should be evenly spaced. Now, if the object is moving, the source, that point, that thing that we're dipping in and out, we'll call that the source. Okay? It's the thing that's making the waves. It's the source, not sources. Source. It's the source of the wave. If we're making that move, the source moves in that direction, then the pattern that we will get is we'll get this sort of thing happening. We will get, and what can you see has happened now is if it's moving in that direction, over here, these waves have got closer together, and those ones on this side have got further apart. Can you see that there's a difference in that distance? So as they're moving forward, they kind of bunch up on each other. They catch up with the one in front of it. And you will see that. And in fact, if you go to the Mindset website, you will see in a series on waves in the real world, you will find that there's a lesson, and I think it's lesson number 3 or 4, that's on the Doppler effect. You'll see in a ripple tank we've done this to show you the shadows and the things. If I've got a chance, I'll try and download it and show it to you in another section of this lesson. I've just remembered it. Okay, so that's the pattern. Notice over here, what we've got is we've got a higher frequency. Why is it higher frequency? Well, there are more things in a shorter space of time. The wavelength has decreased. And here, you've got a lower frequency. They are spreading out. What is this doing? This is moving towards the object. The source is moving. On this side, it's moving towards over here. And if I was an observer over here, it's moving away from me. So it depends. If it's moving towards you, this is what I always remember. If the object or the source is moving towards me, I'm going to experience a higher frequency. That means the pitch, if I'm dealing with sound, is going to increase. I'm going to hear a higher pitch. If it's moving away on this side, the object was moving in that direction, remember, it's moving away, then there's a lower frequency. The wavelength has increased. So, guys, you can read the notes. I'm not going to worry about that. I want to specifically refer now to the equation. And the equation is given in what initially looks like quite a confusing way. I want to break it apart for you so that you can see what each of those things refer to. So, in the Doppler effect, we use the following equation. This is the listener's frequency. This is the observed frequency. This is the apparent frequency. The L stands for listener. Okay? The S there stands for source. That's the thing that's making. That's the real frequency. If everything stopped and we measured the frequency, that's what it would be. So if you look at it, we've got frequency of the listener, frequency of the source. And in between that, we've got the strange fraction. It's a number. That's all it is. It can range from either being bigger than 1, or equal to 1, or less than 1. Now, let's just follow what that means. If we make this green box, so again, I'm going to just create some space. I'm going to go over here, and we said we had frequency of that's observed, we had a green box, and we had frequency of the source. And we said that green box, it could be, if it's going to be that unknown, that little fraction, if it was bigger than 1, if it's bigger than 1, then what's it going to do? That's telling me I must take the frequency of the source and I must multiply it by a number bigger than 1. That means that the frequency of the listener will be going up. Okay? If it was equal to 1, if the frequency of the listener goes up, then we also know from our previous experiment or our previous explanation, this means the source is moving, or the source is moving towards the listener. Now, guys, it doesn't mean that the source only has to move. I could be, as the listener, running towards the source. Okay, so it's relative motion. The source is moving towards the observer. If this big box over here is bigger than 1, then we need to recognize that there will be a small denominator, and this must be relatively larger. Okay? Small number on the bottom, a big number at the top. That's what that will give you. Now, if we find the opposite, we find that this box is less than 1, then what can we say? That we must have a large number as the denominator and a small one at the top. And if we then put it like this, then this is going to get smaller than that. Okay, guys, How are we going to make sure that happens? We make sure by going back to the original equation, and what you'll see is here we've got the velocity of the speed of sound, and we've got to decide, is this plus or minus, or is it plus or minus? And depending on what the situation is, we can then show that the one is positive, the other is negative, or the one is 0 and the other is not. So you must interpret the signs. You must make very clear that you choose the right equation. Remember, this doesn't only apply for sound, can apply, as I said, to water waves, but it can even apply to light. Hopefully, towards the end of the lesson, we'll be able to mention something about light. But for now, I think it's time for a break.
It is, John, but during this break, guys, you have the Test Yourself link. Give those questions a try, mindsetters, and don't guess. Just try and think and then answer them, because you stand a chance of winning this awesome Casio calculator. I'll be announcing the winner after this break. Welcome back, Mindsetters. Now, as promised, I do not just make promises, but I keep promises. The winner for our Casio calculator on a Grade 12 show is Maria Mulopo. Congratulations to you, Maria Mulopo. I hope you're watching the show. We'll be in contact with you soon. So, Mindsetters, you still have got a chance. So make sure that you do the Test Yourself questions in order for you to win this awesome Casio calculator with about 254 functions. How cool is that? So Mindsetters, make sure that you enter right now. John?
Thanks, Abby. Guys, let's get straight into that. And make sure you've got your calculators ready, because we're going to need them for this Doppler effect equation. But you know what? With the Casio calculator, life's a breeze. You'll be able to substitute things in, but please don't just depend on the calculator. You're going to have to do some thinking, first of all. So let's get into the question. And our first question is right here. It's taken from the 2012 exam paper. It's been adapted from there. And it's a very interesting question. So let's have a look at it. It says, a bird flies directly towards a stationary bird watcher. So we're told that the bird watcher is stationary. Remember, stationary means the velocity is 0. So I'm going to put there the velocity of the watcher, of the listener, is 0 meters per second. So I'm breaking it down and I'm adding to it what is important. Also recognize that this happens at constant velocity. Now, this doesn't really happen. Normally birds fly at different speeds. They accelerate, they slow down, they speed up with the beating of their wings. But we're going to pretend it's constant velocity. Else it would be quite difficult to do this question. We're told that the bird emits a sound wave, or emits sound waves, at a frequency of 1,650 hertz. So that is the frequency of the source. The bird watcher hears a change in the pitch as the bird comes closer to him. Okay, so here we are. We've got the scenario. Somebody watching birds with the feathers on, and they're flapping the wings, and it's flying towards him. And what we recognize, constant velocity, the observer is 0, sound is being emitted as it travels towards him, at the same time as the bird is traveling towards him. So we can recognize here immediately, this is a Doppler effect type question. But let's read the rest of the question. Not get too carried away. It says, write down the property of sound that is related to pitch. Well, that's easy. Recognize that pitch is related to frequency. Okay. Frequency, not amplitude. Loudness is related to amplitude. Next thing. It says, give a reason. Very important. Why the bird watcher observes a change in pitch. Now, some people would have just written down, and I know this from marking, that they wrote down Doppler effect. That's not the reason why. Guys, you've identified the phenomena. You haven't given a reason. Why is there a change in pitch? We call the change in pitch, or the apparent change in pitch, the Doppler effect. But the reason why is recognized, and is because there is relative motion between the source of sound, the sound source, and the observer. If it wasn't for that relative motion, there wouldn't be a change in pitch. It's a requirement. You've got to first of all have something that's emitting a sound, and then the sound object has either got to be moving towards the observer, or the observer has got to be moving towards. There's relative motion. Very important that you get that idea clear. So many people wrote down Doppler effect. It's not true. The reason isn't Doppler effect. The phenomena is called Doppler effect. The reason is because there's a difference in motion between the source of sound and the observer of the sound. So here we talk about the air pressure versus distance on a graph is shown below. The waves detected by the word as the bird comes close to him, the speed of sound is 340 meters per second. So now, what does this mean? Guys, we've got to use some thinking here. They're not going to give it to us all on a plate. We're told that over here we've got a high pressure, and over here we've got low pressure, and that started off with zero pressure, that's zero pressure. What we recognize has been this change from high to low to zero, from zero to high to low to zero, in the time or in a distance of 0.2 meters. That's the distance that they've measured these changes in pressure. That's related to the sound. Now, you might not have seen anything or heard anything like this before, but you've got to think about it. Remember, sound is a series of compressions. Compression means high pressure, and rarefactions, which are low pressure regions. So we get high pressure, compression, low pressure, rarefaction, high pressure, compression, low pressure, rarefaction. And the distance between a compression and another compression is going to be a whole wavelength. And we need to make sure that that is followed through. So over here, we recognize zero pressure to zero pressure. That pattern is just like a wave. And so what we recognize is, it tells us from the graph, write down the wavelength of the detected waves. Well, it's not difficult. It has to be 0.2 meters. So the wavelength, lambda, is equal to 0.2 meters. Read it off the graph, we can check it that it's regular and it's fine. Then it tells us calculate the frequency of the waves detected by the bird watcher. Now, if we look at the frequency, we're told here that the speed of sound in the air is 340 meters. Speed of sound. We know the wavelengths. And you should remember that we want to get frequency. You shouldn't remember that velocity is equal to frequency times wavelength. We've been given the wavelength. We want to find the frequency. So let's substitute in 340 times the frequency we don't know. The wavelength is 0.2. Make sure it's SI units. Yes, 340 meters per second, 0.2 meters. Let's divide both sides. And I think I'm going to need a calculator, which I didn't get out. So I'm going to quickly see if I can get it up. And I'll choose it over there. And there's my calculator, my Casio calculator to work with. I'm going to just turn the smart notes off for the moment and take the following thing. 340 divided by 0.2, and we get a frequency of 1700. So the frequency of this observed frequency, because this was from the observed frequency is 1700 hertz. Okay? Just make sure that it's right. Yes, I've got it. Now, what were we given? What was the next part? we were asked to calculate the magnitude of the velocity at which the bird flies. How are we going to do that? Well, guys, we've got the Doppler effect. If you think about it, we've been given the frequency of the source. The frequency of the source was given in the question, and if you look back here, 1670. 1650. 1650 hertz. We've worked out the frequency that is observed, 1700 hertz. We know the speed of sound, the velocity of the sound was 340 meters per second. We know that the velocity of the listener, of the observer, was 0 meters per second. And what we've got to find is the frequency of the source, which is the bird. That's what we've got to do. So how are we going to do it? Let's set it up. And let's make sure that we've set up our equation. What I want you to take careful note. It makes sense. I can check that I've got the right answer. The source was 1650. The listener, 1700. I know the bird was flying towards me, and I would expect a higher frequency. So far I know that I'm on the right track. So let's now set up my equation, and I'm going to write down the equation just as it is on the data sheet. So it was that funny fraction which just said V plus or minus V, and I sometimes forget it, so I'm just going to make sure that I've got it from the data sheet, and it was back in my summary note over there. It was VL on the top and VS on the bottom, and you really need to know that. I just slipped from my memory for a second, and it's fine to check. V plus VS, and over here VS. Okay, excellent. So now what are we going to do? We're going to start to substitute in. And we're going to say, what was the frequency of the listener? Well, the frequency that the listener observed was 1700. What was the velocity of the speed of sound? We can say 340. What was the velocity of the listener? No, that was 0. So we could do plus or minus. It doesn't matter. Now, guys, here is the important thing. The frequency, let's just fill in the next one. This is 340 as well. Now, what do you need to recognize? To make this bird, to take into account that the bird is flying towards you and that the frequency is actually increasing, which we've seen, you've got to make the denominator smaller. So we added 0 on the top, so we must subtract VS on the bottom. That's what we're trying to find. Otherwise, it's not going to work, because we want this denominator to be smaller so that the number, this factor, remember our green thing over here, must be bigger than 1. We must be bigger than 1. To make it bigger than 1, we must make the denominator smaller than the numerator. So, what was the frequency of the source? Let's fill that in. We know it was 1650. Now, how are we going to solve? Well, at this point, the maths is done. The physics is done. It's just a little bit of calculation, a little bit of substitution and manipulation. If you get as far as this, don't get bogged down. It really is not difficult. So the first thing we're going to do, that I'm going to do, is I'm going to multiply both sides of this equation by this denominator, because I want to get the unknown to that side. So I'm going to do that, and I'm going to say I want 340 minus VS in brackets times 1700 is equal to 340 in brackets times 1650. Okay? Be very careful that you don't make a silly mistake. The next thing you're going to do is 340 minus VS is equal to 34 in brackets 1650. We're just showing it. Divide both sides by 1700. And now the last step that we're going to do is we're going to say to ourselves, let's add 340 to, let's subtract 340 from both sides, and we'll get minus Vs is equal to this whole thing, 340 times 1650 over 1700 minus 340. Now, some of you might have wanted to use your calculator sooner. That's fine. You can do that. I've left it to this point. Don't forget your minus sign. But at this point, I'm going to leave it there. I don't want to lose it, but I don't want to use it just at the moment. Let's deal with the fraction first of all. Now, on the Casio calculator, we've got this lovely fraction tool. I think that these questions, this Doppler effect, is an ideal place for you to use the fraction button. And so that's exactly what I'm going to do. I'm going to say 340 multiplied by 1650, then underneath on the denominator 1700. Make sure that you've got everything in there, and then I'm going to subtract. I'm going to subtract 340. Now, here's a prediction. Because I have a negative on that one side, I think this is going to be a negative answer. Let's see what it says. Yeah, negative 10. What am I going to do now? If I get this answer, guys, be very careful. We said Vs is negative 10 meters per second. What does that mean? Do we have to say opposite? No, no, no. Just divide both sides by the negative, and we can say, therefore, Vs is equal to 10 meters per second. We don't need to give direction because the question asked us for magnitude of the velocity. So the answer of 10 meters per second is quite adequate here. Okay, let's see if we can do one more question. And although these questions sometimes take a little time, I hope you can see the pattern. I'm going to try and point out the tricks and the things for you to look at. Now, notice question number 2, a car is stationary at a green traffic light. A taxi sounds its hooter as it passes the car at a constant speed of 25 meters per second. Now, 25 meters per second, that's quite fast, because 20 meters per second is about 72 kilometers an hour. Taxi shouldn't have been driving that quickly. At a robot, we're in a public area, in a built-up area, should only be doing a maximum of 60 meters per second. So the taxi's not behaving well. The hooter has a frequency of 256 hertz. So there's the scenario for you. Now, it's assuming the speed of sound is 340 meters per second. And simply what it says is calculate the frequency that the driver of the car hears as the taxi approaches him. Now, that is very important. The taxi is approaching him. What does that mean? We can expect the frequency to be higher. So, put down the equation. VL is equal to V plus or minus V listener over V plus or minus Vs, and we put down the frequency of that. Guys, what can we substitute? We want to know the frequency of the driver. We want to find this one. I'm going to do a quick substitution here. I know that the frequency of the source was given as 256, so I can put 256 over here. The frequency of the velocity of speed of sound was 340 plus 0 because the listener wasn't moving anywhere. Now you have to decide, is it the 340 plus or minus? Well, it must be minus because it's moving towards him. So we're going to say minus the speed of the taxi. And we were told the taxi is moving constant speed of 25. So we must take out 25 and put that in. And I'm going to leave you to use your calculator to get an answer. Check that it is a higher frequency than 256, then you know you've got the right answer. But for now, over to you, AB.
Thank you so much. Mindsetters, you have the test yourself and the challenge question. It's on the wall. Post your answers on the wall post that says challenge question. Mindsetters, please. It's on the wall. Facebook.com/LearnExtra. After the break, I've got exciting news just to share with you. So stay tuned. Welcome back, Matrix. Now on the page, the exciting news are I have shared with you a link for the past exam papers. Look through them, and then, as John said, you will never go wrong also. But now, John, there's a question.
Okay, just before we get that, guys, I need you to know that not all the past exam papers have all the questions that are relevant for your exam. Remember, you are going to be writing the CAPS exam paper, and some sections of physical sciences are no longer examined. So please make sure you check the exam guidelines and make sure you get those from your teachers. I'll also get AB to post a link to those exam guidelines. Study the exam guidelines religiously. Don't move away from them. And make sure you only practice those questions that are going to be in your exam. It's a bit silly to spend hours and hours on questions like diffraction and interference when they're not going to appear in your paper. But Doppler effect, yes, it is in the paper. Okay,
All right.
So the exam papers are important, and you know what? You can even go to the shop, the Mindset shop. AB will post you the link, and you can buy a booklet, for less than 100 Rand, I think it is, that will give you all the previous exam papers with the memos in a booklet, and that's a really good investment.
Again, I say you're a prophet. You're a prophet because Sianda inboxed me on Facebook saying, but where can we get books that are published by Mindset? We need physics textbooks.
Okay, so there you go. It's shop.mindset.co.za. AB will post the link for you. So just make sure that you get those on. Go on. You can order online, and it will get delivered to you very quickly.
Awesome, John. I have this question, John.
Yes.
The Mindsetters are asking, why can't they have extra lessons on weekends, especially on Saturday?
They want Learn Extra on Saturday. Well, guys, Learn Extra is on Saturday. Maybe you've missed it. It's not live shows, but it's great revision lessons that we've put together for you. But there's a slight change for those of you that have been tuning into the Learn Extra live, the Learn Extra lessons on Saturday. There's a slight change in the schedule. And it might make you feel excited. I hope it does. Some of you might think, oh, no, not more of that. But we think it's a good thing.
Exactly.
Tell us the news.
The news are from 11:30 to 1 o'clock, we have the live schoolboy rugby. So for all the rugby fans, we're going to be having a live
that's amazing.
Schoolboy rugby.
And you know what? I heard that it's a real derby match. That means it's a really important match. Those of you that perhaps haven't heard about rugby, don't play rugby, it's something useful to watch. And there's great spirit. You'll see the teams cheering each other, the cheerleaders being... And this weekend, it's...
This way, it's the Sacks versus the Bishops.
Sacks and Bishops. That's a huge game. So, guys, if you can't get down to the game, if you're watching in Cape Town, and for whatever reason you haven't got transport and you want to support your favorite side, maybe your dad's an old boy from Bishops or Sacks, and they'd like to watch it. Maybe you're going to be playing Sacks or Bishops in the next couple of weeks, and you'd like to see what their fancy moves are. Hey, record it, watch it, and join us. But that means that we've got to change our Learn Extra lessons schedule around. So normally we have math starts at 9 o'clock, so there'll still be maths. It will run till 10:30. Normally we'd have physical science from 10:30, but it won't be physical science from 10:30. We'll just have a lifestyle program until 11. Is that right? Until 11 o'clock?
Actually, our physical science starts at 1 to 2.
Yes, that's what I'm saying.
Yes.
So it normally starts at 10:30.
Yes.
But now it's going to move out until 1 o'clock. So instead of 10:30, it's 1 o'clock. So please take a note, tell your friends, join us at 1 o'clock. We'll be doing physical science, or join us for the rugby. What time does the rugby start?
The rugby is from 11:30 to 1 o'clock.
11:30. So join us at 11:30 for the rugby.
I think I should be a cool guy and then just post the schedule for the Mindsetters.
Absolutely. Do that for us so that we've got it all sorted. Okay.
Cool.
So guys, let's get back to our question. I hope you got your calculator. I hope it was a Casio calculator. If you haven't got it, Casio calculator, enter the test yourself. See if we can get you one. So I've used the fraction button. filled my values in, 340 on the numerator, on the bottom, the denominator, 340 minus 25, multiplied by 256, push the equal sign, and now it gives me a common fraction. I don't want it as a common fraction. Don't write this down on your exam paper. The examiners will not be happy with you. You've got to push the simple to decimal button, and it tells you 276,31. I'm going to round that up to 276,32. So 276,32, write in my answer, 276,32. And don't forget the SI units for frequency are hertz. Let's just quickly finish this question so that we have got it clear. It says now, how will the observed frequency of the hooter change as the taxi moves away from the car? Now, look at the instruction. Only write increase, decrease, or remains the same. Well, as the taxi moves past and it starts to move away, the sound source is moving away, so it will decrease. Okay? It then tells us to explain briefly your observation in 2.2 in terms of distance between the source and the observer and the wavelength of the waves. So what we're going to say, as the source, the distance increases between the observer and source, we say the wavelength increases. Okay, you can draw a picture to show you that and illustrate that, but that's exactly the thing. One of the applications of the Doppler effect is ultrasound. What is the advantage of using ultrasound as opposed to X-rays in medicine? Well, ultrasound is not harmful. It's not harmful. And it's slightly less expensive. It also can deal with soft tissues. So things like blood, it's very specific. Even an unborn baby can have an ultrasound to see exactly what's happening. Whereas high energy, penetrating, ionizing, electromagnetic radiation like X-rays can do harm to our body. Okay, AB, I think it's time for the challenge question.
Yes,
so
John.
let's get into the challenge question. We're going to have a look at it. So, has anybody got an answer?
I have some answers.
Okay, let's see what they've got, and let's see how it compares to my answer, and see who's got it right and who hasn't. Again, it tells you 340 meters per second. How fast must the car go for a person standing on the side? So the person, the observer, was 0, and the is 15% higher than the pitch. Okay, so than the actual pitch. Now, guys, the problem here is that they haven't given you the frequency of the pitch of the cars. So I'm going to choose something. I'm going to say, let the frequency of the source equal X. That means that the frequency of the listener must be 15% higher. Now, guys, what do we do to get 15%? We know 15% is 15 out of 100. So if I want to increase something by 15, I'm going to say 15% plus 100% to give me 115%. And 115%, if I write it as a decimal, is going to be 1,15. So I'm going to say that if X is the frequency of the source, then 1,15 of X is the frequency of the listener. That's what I want it to be. Okay? Now, let's see what we want. We want to find the speed of the car. So let's put our equation together again, and I hope you're seeing the pattern. The frequency of the listener is equal to the box, the fraction bit, times the frequency of the source. What's in the box? Please don't draw the box in your exam, but I want you to think about it as the box. It's that fraction bit. I just want to erase it a little bit better than I did. So let's do that. And let's put the box into a different color. We're going to say we're wanting this bit, which is the velocity plus or minus the velocity of the listener, the velocity of the sound divided by the velocity of the source. We've done one very similar to this in the first question. So it shouldn't really be a surprise to you. The only difficulty is the part where we say this is 1,15x, and this velocity was 340. This one was 0. Now, notice what was happening. We read the question. How fast was the car going for a person standing on the side to observe a frequency higher? So if that is higher, then that means that the denominator must be smaller. So it's 340 minus the frequency of the source, okay, the velocity of the source. And then we're going to say, what's the frequency of the source? And we're going to put that back into, let's keep it as green, we're going to say that as x. So the first thing I'm going to do is I'm going to divide both sides by x, and that should give me 1,15 on this side is equal to 340 over 340 minus Vs. So now you can multiply both sides by 340 minus Vs is equal to, divide by 115, 340 divided by 115, and just substitute into the calculator. So let's do that. We get, let's do, first of all, just get the like terms onto the same side. We can put 340, 115, minus 340 on this side, and I'm going to put that all in brackets and put a minus sign outside there, and I didn't do this last time, take away that minus sign. Let's see what that works out. It should give me a positive answer. Hope it does. Let's check it. So first thing I'm going to do, I'm going to put a minus sign, put a bracket, put the fraction 340 divided by 1,15. Next one, minus 340. Close the bracket, push the answer, and we get 44,3435. 44,35 meters per second. 44,35 meters per second. That's moving really quickly. I don't even know if that's possible realistically, but it looks like that was the answer that was required for the challenge question. So let's see. Did anybody get it?
Yeah, we have two mindsetters that actually got it. Okay, it's one. The other one missed the -1 at the end.
Second to the minus one. Or did
Yeah.
they just put MS? Oh,
Yeah.
that's a typing thing on Facebook. I'm sure they actually meant it. But guys, please be careful. Don't make silly errors. Now, AB, any questions?
Here's one question from Pilisizwe Kunene. Can you please explain when the denominator is bigger or equals to 1 on the equation?
Okay. We've looked at examples where objects were moving towards. So here was the source. And in all the examples that I've done tonight, the source was moving. I don't know why I keep on saying sources. It should just be source. The source of the sound was moving towards the object, and so, or the observer. So we had the observer here, and the source was moving. And in this scenario, you would get a higher frequency. And a higher frequency means that when you look at the equation, you're going to get V over V minus Vs. Okay? That's what that means. It would also mean the same if this one was stationary. The other scenario that it could be, if the source was stationary. So let's just sketch that and say if this was stationary and the object was moving towards it, then we would get the following. We would get V plus V observer over V. Now, I hope you can see in both those scenarios, the denominator is smaller. the denominator is smaller. Has to be smaller. What you're asking, and the reason that is the case, it's a higher frequency. So let's sketch what will happen if we get a different scenario when the source is moving away or the person is moving away. So let's start with this. The source is over there. That is the sound or the light, and it's moving away. And this is the observer here. The observer is stationary. The VL is 0. So watch what's going to happen here. Because it's moving away, we know that the frequency is going to be lower. The frequency is lower, is less. That means the pitch is lower. Frequency is less, the pitch is lower. The frequency is more, the pitch is higher. Okay? Get that terminology right. Then in our equation, what we're going to have in that fraction bit, just the fraction bit, we're only interested in the fraction bit, what's going to happen? Well, have a look. The V is still there. This is 0. Now, to make this smaller, the denominator's got to be bigger. So we've got to add plus the velocity of the source. Now, that's the one scenario. Very quickly, what would happen if the source was stationary and the observer is moving away? So we're getting this scenario. Then the equation would look like this. V plus, oh, sorry, not V plus, and that was the key point, that this denominator must be smaller, the numerator must be smaller. So it must be V minus VL over V, which if that was plus 0. So in both these cases, the fraction will be less than 1. This will be less than 1, that will be less than 1. If it were equal to 1, will happen when both objects are not moving. Okay, is there anything else?
Last one. It seems like the mindsters got confused on the challenge question. They said they don't understand how you converted the percentage in the challenge question.
Okay, let's go to this. I want you to understand what 15% means. So if it says 15% higher, now guys, I know that a lot of you don't do Maths Lit, but I know that on Maths Lit programs, Peter and myself have gone over this. So please be very clear about it. Watch the Maths Lit if you're not sure about working with percentages. 15% means more, means 115%. Because it's 100%, which is what your initial is, plus the 15%. And 115% is 115 divided by 100. And that gives you 1,15. And that's what you need to do. Okay, over to you.
Thank you so much, John. With this 8 seconds, messages, thank you so much for tuning in. And remember to watch our shows tomorrow, even though it's a holiday. We love you and peace.